Thanks for taking the time. When I see that other people are interested in talking about misinformation, talking about how to figure out what to believe online, offline, it's hard. It seems harder and harder nowadays, right? It's just, we're overwhelmed. We're inundated with information all the time. And I feel bad for the younger generation because they have a lot harder time than we all did, where there was at least a less options to look for. So what I'm hoping to accomplish today is to hit a few points around this challenge of discerning what's more reliable, or at least tends to be more reliable than other kinds of information when it comes to science. Now, science is something we should all be accessing all the time. You don't have to have a PhD in science to engage in science. Of course, we're all scientists. We're observing, we're asking questions. But we, with our taxpayer dollars, pay scientists at great places like the University of Washington to do research. And if you have a question about Alzheimer's, you should be able to access the latest, greatest primary literature around Alzheimer's. And so what I want to do today is talk about the ways in which you can navigate that information world if you're trying to access science-related information, or you hear science-related information on the web or from the CDC or from your neighbor who is interested in similar kinds of things. And I'll say this from the very beginning. It's not easy, even for people like myself and Eric who live and breathe science. This is what we do every single day. And it's still challenging for us. One, because the literature grows so fast, I can't even keep track of my own very sub field. Thousands of papers. Well, thousands is not even a really good characterization if you look at the whole literature. But let's say tens of thousands of papers are being published every single day. And there's just no way to keep up with it. And especially now with AI, large language models, and chatbots, and the ease in which it is now for authors and even non-authors to create content, it's harder and harder to discern what's real or not. So my goal is to do a little bit of trying to answer a little bit of this question. Now, I have thousands of slides of lectures related to this topic that I, of course, can't get into. So I'm just highlighting a few kind of current things, and I'll hit some of these issues around AI. I'll try to answer some of those questions that you were given beforehand. They're not super easy. I'm going to push you a little. Hopefully you can push me to make sure that I answer those questions at the end. But yeah, so just before we get started, this isn't easy. So if there are some things that are kind of new and foreign, or you're not even quite sure, then that's okay, because it's hard for us even in science. And for those that have a little bit more experience, maybe you had a former career in science-related areas or in research, you might be able to help all of us sort of discuss how you work through some of these challenges. But let me first start with a slide about the remarkableness of science, because most of this lecture is going to be about ways in which you might be misled by science that's not so great. So I need to start with two slides, what's basically one slide, about the magic of science. Despite some of the things I'm going to say about science today, which is both, to inform you, but to also let you know that science isn't a perfect institution. It also has challenges, and it doesn't always get it right. But despite all that, we have technology like CRISPR-Cas9, which has this, for those that are familiar with this, it's this remarkable technology that came out of science labs. Actually, I've spent the last year, this year at Berkeley, and Jennifer Doudna is there. She's the person that got the Nobel Prize in this and shared it with some others as well. But it's this technology that allows the world now to edit to a very fine degree, very precise locations of DNA to insert or to remove things that can help people that have genetic diseases or have other issues. And just to be able to do that, to go into, first of all, even to be able to go down at these very small scales, edit, and then potentially make fixes that can help people's long-term health is just remarkable. So I wanted to start with saying that science is amazing. I've been one of the biggest, I'm a huge fan, like many of you probably are. Ever since I was a kid, I've always been fascinated by science. And despite some of the things I'm going to talk about today, it's amazing. So that's about all you're going to get in terms of really good science. Now I'm going to talk about some of the ways to discern some of the less reliable science from the more reliable. But before I do that, I want to introduce you to who I am and what I do as a researcher. I spend most of my research days and nights in the darker corners of the internet. And that can give you a depressing view of the world sometimes. So I have to come out to things like this and go, oh my goodness, we can just I can talk to real people that are interested in learning. What a joy. These are the highlights of my week for sure. But in doing that, I spend a lot of time, of course, looking at the ways that rumors spread, the way that bad state actors spread misinformation purposely, so disinformation, there's an intentional element. But in all those conversations, there are the things that I spend a lot of my time studying and trying to understand is related to science and health information. And so that's what I do for my research. I spend a lot of time thinking about how misinformation spreads, how we can mitigate it, how technology is a mediator in that, and then thinking about how that relates to what we can do in society in terms of policy and education, community engagement. And I will say from the very beginning, studying misinformation is challenging. My colleagues and I have been attacked, through litigation and other kinds of forms over the years, just because it is a topic that gets people excited in good and bad ways. And I'm not here. I say as a researcher, I'm never here to tell you what is true or not. That's not my job. What I do as a researcher is I study the ways in which communities disagree on topics, and sometimes those disagreements or beliefs might go counter to the consensus in science. And so that's how I think about misinformation. I'm not a fact checker or a journalist. That's fact checkers and journalists' jobs. As a researcher, I study the ways. I essentially study disagreement. And so that's a different way of approaching misinformation. A lot of times people think, well, how do you know what's true or not? Well, I have my own methods for how to discern what's true or not. And I'll talk about that as an individual and as a researcher and as a citizen that tries to navigate information. But when I study this, I study it zooming out, and I look at this more from the standpoint of how people do sense making more generally online. All right. As Eric mentioned, my colleagues and I started a center that's devoted to this topic that is here at the University of Washington. And I'm biased, of course, but I do think it's one of the leading centers in the world on this topic. And we've had it around since 2019, like it was almost minutes before the pandemic, but we've also been doing this work far before we started the center. All right, I have this book that I sort of talk about how you can empower people to do these sorts of things, and a class that I've had a lot of time teaching, a lot of fun teaching. You can go here. A lot of the material is free, and I'm adding more material all the time with my colleague, Carl Bergstrom, who is my conspirator in teaching this class on campus. It's always been, it's been fun. Students love to call BS. And so that's been an exciting little teaching endeavor. Now, a lot of what I'm going to talk about comes from a paper I published in the Proceedings of the National Academy of Science, which talks about misinformation, not only in society, but also in science and about science. Now, again, just like I said in that CRISPR slide, it doesn't mean that science is broken. Science still works remarkably well, but it has some issues that's made it harder, actually, to discern what's true or not. And so my goal for you is to deliver some of those things to watch out for. So let me start with a story. I love this graphic, by the way. This is just a fantastic graphic that captures so much of what we were challenged with during the pandemic, and certainly before the pandemic and after the pandemic. But I've been working with clinicians that have been doing not just medicine anymore, but have been having to talk with patients like half their time or even their whole meeting with a patient about something they saw on Facebook or something that they saw on social media or read. And that's a new challenge for doctors. And what they're seeing is that misinformation is not just some common annoyance online. It's something that affects people's health. And so I've been having conversations over the last year with lots of these different groups. And one story among many that has stuck with me was a story during the early parts of the pandemic at a hospital not far from this university. And the emergency physicians in that hospital on one of these days had a patient come in with their arm literally hanging from the elbow. Blood was dripping from bandages. It was a construction accident. And the doctor said the protocol, at least at this point in the pandemic, this was early in the pandemic, the protocol was that everyone coming into that hospital had to do a quick nose swab test of whether they had COVID or not. So then they could have different protocols for that. And this patient refused to do this because this patient had been reading online that the sterilization agent of these nose swabs caused cancer, ethylene oxide, which it doesn't. I can tell you that from the beginning. But what's interesting about that particular rumor, and this is a false rumor, some rumors are true, this was a false rumor. This particular rumor had gained a lot of traction online. This patient had been pulled into these conversations and believed it so strongly that those doctors could not convince the patient to come in. The patient turned around. It was the last those doctors ever saw this patient as this person was dripping with blood leaving, because they believed so strongly that a nose swab was going to cause cancer. This became such a problem in the state of Washington that they had to create information campaigns and flyers on ethylene oxide. A lot of you maybe have never heard of ethylene oxide. You're like, what's ethylene oxide? I would have never predicted before the pandemic began, or even during the early parts of the pandemic, that we'd have to have an information campaign about ethylene oxide. Here's the information campaign. It says here, ethylene oxide sterilized nasal swabs are safe and will not cause long-term health problems, et cetera, such as cancer, et cetera, et cetera. Instead of focusing on maybe some of more of the important issues at the time, they had to focus on this because this was something that had gained steam online and affected behavior. It affected this individual that had gone to the hospital and many others. So the point I want to make here is that misinformation is more than just a common annoyance. It affects people's behavior. It has effects, and we have to take it serious. Now, it's not so easy and straightforward on how you go about doing that, but that's one important lesson that I've learned in studying these issues that deal with science and health, that it does lead to behavioral change. And that's why it's important. Now, we're going to move on to the next lesson. I'm going to talk about this, and this is actually one of the questions, excuse me, is watching out for what are called data voids and being aware of this argument around evidence. What do I mean by this? All right. First, data voids are this scenario where there's a huge demand for wanting to know something. So in this case, it was ethylene oxide, a huge demand, but very low credible evidence because the health industry or scientists or researchers haven't had the time to address that particular topic yet, because they're dealing with all this other debunking and all this other fact checking and all this other community outreach to address health issues or science issues. And data voids are taken advantage of by those that are sometimes purposely pushing disinformation campaigns. This comes from bad state actors. This has been shown many times from Russian agents and other things, and other foreign adversaries, but even internally sometimes, where you can find a topic that doesn't have a lot of credible information around it, and you can then create essentially what seems to be something people are all reading about, and then it shows up high on search engines. So when you search it, there's no one's done any credible fact checking, so that's all that shows up is the poor information on it. So again, data voids are a situation where there's high demand, but low credible information. Let me give you an example. So we do this game in my lab sometimes where we essentially say, okay, find a question or input a question on Google where you cannot find an answer. It's very hard. It's almost impossible. It's so hard that when a student finds something, I'm like, no way. We did find one the other day. And I'm like, oh my gosh, 0 results. That is amazing. But for the most part, you're going to find evidence for anything you want. That's where it comes this infinite evidence issue, that it's not about evidence anymore. There's infinite things out there. It really is more how you parse through your sources and come, and how you come to the table with your argument. But that's not usually what's talked about. It's like, I've got evidence because I Googled it. I did my research. And by the way, I encourage everyone to be researchers and to be their own scientists. This is good. Citizen science has been a great movement in science more generally over the last 10, 15 years. But I want people to be aware of these data voids. So we did this question. I'm going to give you examples. So with all this talk around vaccines, there is all this attention around it and demand for these questions. And so my colleague and I thought, Carl Bergstrom, who I had mentioned, thought, well, there can't possibly be any websites or links between vaccine safety and, say, shaken baby syndrome. Shaken baby syndrome is very clearly shaken baby syndrome that happens, unfortunately, with some parents, and it has ill effects. So we thought, okay, do vaccinations cause shaken baby syndrome? Now, we can have discussions about vaccine safety and issues and how they affect different people. We can, we can have those discussions, but you wouldn't think there would be a connection to this, right? Well, there are lots of websites. As you can imagine, dangerous vaccines found to cause symptoms of shaken baby syndrome, national vaccine. There's all these things that you can find. And then if someone looks at this and says, look, I Googled it and I found these websites. So you have to be aware of these data voids. So we need to change the conversation from evidence, even though, of course, we use evidence in science, not to say that we throw evidence out the door, but in this new world of information overwhelmingness, we need to move from those conversations of just evidence to rules of how we came to that evidence. So where did you get it? Oh, you got it from Google. Okay, so then what are things that can go wrong with Google? Things like data voids. Like when my kids ask me, or they say, oh, I found this thing on YouTube, it must be true. I'm like, well, who's telling you that? How do they know it? What do they have to gain from that? These are the kind of basic questions that we've all known growing up in the world, but we need to have more of those rather than just subscribing to, well, I have evidence online of that. And my hope is that we could actually bring civics back to education. It's one thing that's been out. Wouldn't that be great? I mean, I know some of you are like, yes, and especially digital civics. And to talk about things of how do we know what we know, in addition to all the other civics lessons that used to be taught in schools, but aren't anymore. And I know there's a packed schedule and curriculum already, but I think it's really important that we bring back digital civics. So if you can push your legislators to bring that back in some form, if not at least in informal environments, I think would be important. So watch out for data voids. Misinformation is more than just a common annoyance. Now, retractions. Now, in science, we have retractions when it comes to general, traditional media. A newspaper might publish something and then retract something because something is wrong, and they'll have corrections, which is great. In fact, I tell students, if you're going to a news outlet and you've never seen an admittance of a mistake, something's wrong with that particular news item, because everyone's going to make mistakes, and we have mistakes in science. The problem is we don't do a very good job in science in formalizing and tabulating when retractions do occur. So if you're citing a particular article or using a particular article to make an argument, one of the basic things, I know it sounds so basic, but we need to teach the public in science and in science itself where to look for those retractions and ways in which publishers are finally allowing us in 2024 to note when there are problems with a particular article, whether there was methodological problems or there was issues with the data. And I need to just make it very clear that not all retractions are done because of nefarious intent. Now, there are examples like this. There are examples of fraud and other things that come out. But what more often happens is there's just mistakes. Humans are the ones running science. It's not just some robot that doesn't make mistakes, although we know our newest robots, AIs, make mistakes all the time, so hallucinations and things like that. But when we make mistakes, we need to make it clear that they are. So let me give you some examples. So there's been a lot of discussion recently and over the last 5 years or so around this epidemic, this like fentanyl epidemic, this opioid epidemic, et cetera. And what's interesting, if you look back at the history of this, of the use of some of these drugs, both in formal settings, clinical settings, and also, of course, even how that then relates to how it transferred to what's happening on the streets. There was a paper that was cited a huge amount as evidence or as like support for giving patients some of these pain medicine. And this is the paper. You can't read all of it, so I'll just describe it. The thing here is that this was an early paper that was published back in, I'll have to look exactly. It looks like 1980, quite a long time ago, but it was quite influential because it basically made the claim that addiction was rare in patients treated with narcotics. And so it was cited a huge number of times. But the problem with this particular article is it was on a very, very small number of patients, and it had some other issues, but it continually got cited. And then that citation led to more citations, the rich got richer sort of thing. And it became such a problem for the field that the New England Journal of Medicine had to put this little note at the top, and you can't read this, and that's the problem. I want it much more bold. that for reasons of public health, readers should be aware that this letter has been heavily and uncritically cited as evidence that addiction is rare with opioid therapy. And then there's a description from the editors there. So great that we have this little banner, but this banner just recently went up. Up until even just recently, there was no way when you came to an article, whether you were a scientist or a non-scientist, to tell whether this was an article that had problems with it. So we're just barely getting to the point where we now have banners and some, but it's still not, only a few, not a lot of journals still do this. But the point here is that we have to be aware of both formal, this wasn't formally retracted, the article still stayed, but we have to be aware if we're starting to use an article a lot to make a point or a new policy or a decision by our own self around our health, that it hasn't been, that it hasn't had some real serious problems with that. Now, some are actually retracted because there are. Now, this one isn't retracted, but the point here is that you have to kind of look carefully for these kinds of things. Now, what's interesting about this particular paper, which this one hasn't formally retracted, but we can sort of place it in that particular category. If you look at the analysis of papers that cited it, even after this issue came out, so OxyContin was introduced here, even after it was noted these problems, it was continually cited in the affirmation, so the darker color, over time. These are by researchers themselves. So they're citing it in affirmation, saying that it was evidence of low addiction in using these narcotics. And it continues even up till, it's going down more now because of a lot of the attention that's received. But the point is, if the professionals in the field are misciting this particular paper, no wonder the public would have a hard time trying to understand that. Now, and this is not just, this is not a rare thing. It's all over. And I'll just give you one other example because it's an example that does really matter in oncology. So this is a paper that shows continued citation of retracted radiation oncology literature. So this paper looked at all these papers that have been formally retracted. It wasn't just like, be careful of this paper. It was retracted and it continued to be cited in the positive over and over. And if you look at a lot of these papers, there's been a whole bunch, and we have some work that we've done in the center ourselves looking at some of this, a large number of retracted articles continually get cited in the positive, even after it's been formally retracted. So as a reader of the literature, be aware, make sure if you're using a paper as evidence to make a decision about your health, that it hasn't been retracted. And you can go to places like Retraction Watch. That's probably one of the best resources. They do a great job. It's essentially a nonprofit that was formed many years ago that tries to keep track of these for the public. And they don't give enough credit for the work that they're doing, but they're watching for these retraction watches and then these retractions and then make them public available. But they don't track everything. But anyway, if you're going to engage in the literature, that's one of these tools you need to have in your tool belt. Okay, so check for retractions or editor notes, things like that. Now, it's not a dirty secret of science. It's just sort of I guess it's an expectation. Not all journals or conferences that you see scientific papers are all the same. Now, that seems pretty obvious, right? But they are very different when you start including things like predatory journals, which I'll talk about in just a second. So a month or so ago, Andrew Gelman, who's a very famous statistician at a Columbia University, put out this post, and I was aware of this situation too before, but seeing it come on Andrew Gelman's post it's very scary in the field if you ever get a post by Andrew Gelman calling someone out, because it means he's probably right about this. But there was an unfortunate finding by a dean at this particular university that had been publishing what seemed to be fairly low quality papers. And this is sort of ongoing, and I don't know what the latest news around is, but the point here is that even those at the highest level, this is a dean of the engineering school, was publishing a whole bunch of stuff that wasn't very low quality. And just to demonstrate the low quality of this, I just wanted to show you a couple examples in his own journal. This is his own journal, publishing himself. This is a paper that is supposedly looking at using science to minimize sleep deprivation that may reduce train accidents. And if you look at the study, he talks a little bit about, it says, Big findings like our recent study has the premise that both humans and flies sleep during the night and are awake during the day, and both species require okay, you're listening to me say this. You think, okay, this is setting up a paper, right? Well, this is the full paper. This is by a dean leading other researchers and other PhD students and other researchers. Now, he's been called out, and hopefully this gets addressed, and hopefully he sees this as a mistake, and I don't know what the university is going to do about this, but this is not all that rare. And so when you see what looks like a journal, ICT, whatever this journal is, there are thousands of journals that say they are engineering journals or science journals. They are not the same. Now, I showed you the New England Journal of Medicine before. They still make mistakes, but New England Journal of Medicine has been around a very long time, and it is more reliable than others. So the question is, where do you then go to tell whether a journal is more reliable or not? Well, first of all, I'll just say a couple of things about predatory journals. I don't know necessarily, it's hard actually to define what a predatory journal is because there's a whole continuum. But predatory journals tend to be journals that have little to no peer review. And that's one of the key elements of science. They have editorial boards. They have editorial boards because those editorial boards, and academics have played some jokes on these probable predatory journals by putting actors, John Wayne, and, I don't know, all these names that are just, actors that aren't, of course, scientists, and show how easy it is to get these people on these editorial boards. So they have editorial boards. They just don't have much peer review. And by the way, it doesn't, and, just because a journal is for profit doesn't mean, there's for profit. Predatory journals are essentially trying to make money off of this movement into what's called open access. So in science over the last 10, 15 years, there's been this movement to change the model that supports publication. And it used to be that our libraries here at the University of Washington paid for all the journals. So Eric and I would submit a journal or a paper to a journal. It would go through peer review. If it's accepted, then it would get bounded. And then libraries across the world, they then subscribe to this journal, and then we get access to that. Unfortunately, you in the public, if you're not associated with the university, wouldn't get access to a lot of the good literature out there. So there's been this movement, this open access movement, which I support, but has its problems. The newest movement, about half the literature now, we published about how much of the literature is in our recent paper on this, shows that about half now, approximately, is open access. Now, the way the open access world works is that either universities can pay into these consortiums, or the author themselves can pay for the article then to be available as soon as it's published to the public. And that's what we want. We want these articles to be available to the public. And that's a good thing. But people started to realize they could make money off of pretending to be a science journal, taking advantage of the incentives in the academic system to publish. So what these publishers did, and by the way, the US has sued some of these journals. Some of these journals have been these publishers, their publishers are a package of journals. But these publishers that were essentially not doing peer review, that had very low quality paper, some of them might be high quality, but they were taking advantage of the fact that authors wanted to get their stuff published and show their deans that they're publishing. And so they pay the $2,000 or whatever, even though the costs have gone way up. So to publish in Nature Human Behavior, it's about $10,000 from an author's pocket. So it's not perfect, but at least it's available, and that is a higher quality journal. But they're doing all sorts of scams, like predatory journals are then even taking papers that have already been published and putting it in their journal and doing all sorts of things. And so you need to be on the lookout for predatory journals. There aren't a lot of great lists. There used to be a list created by a librarian at the University of Colorado. It's called Bill's List. And it would say, these are probably publishers to avoid. But unfortunately, that project stopped, very likely because of maybe litigation and other things. I can only speculate. I don't know exactly the answer to that. But it has become a pretty serious problem in the academic publishing. And so you have to look out for that. If you're engaging with the literature and you're getting a paper, you need to, there are resources. Like we have a website called eigenfactor.org, which you can go and look at journals that have been at least listed in what's called the Web of Science and other places where there's been some vetting. It's not to say that they're all perfect, but they're at least curated a little bit. So I guess here's the thing. Don't assume because something looks like a science journal that it's reliable. But then you're like, Jevin, that makes it hard. Like, it's already hard to figure out where the good science is. And now you're telling me I don't know if I can trust what journal is better than not. Well, that's where you can go. I'm going to show you in just a second. I'm going to come back. I provide some tips here. So my colleague and I, Carl, wrote this. So how do you know if a paper is legit? Now, it's not perfect. And as I talk about it, it's very challenging to even go through that. But if you go to this link, and I can provide these slides and everything afterwards, it gives you at least some clue because it's not easy. I can tell you as someone even in science, sometimes I'm like, I've never heard of this journal before. Can I trust it? When was it? One of the questions you can ask is, when was it established? Where is its location? Not to say that you would like not trust a journal necessarily from India, but there's been quite a few predatory publishers that have come out. And even India's government has called out some of those publishers. The US has sued a couple of those. Just take an extra step, I guess, is the point. And we're working in the field on trying to make it easier for the public to understand at least top-tier journals and journals that might not have some of that peer review. Now, peer review doesn't make it perfect. Peer review is not a perfect process. I wish it was, but at least it's something. At least it's one step with experts within the field. Okay, now let me go back to the next issue. What you're looking at here is one of the most shared articles of all time on the web. We can track these kinds of things. We can see where they land in social media, where they land in different languages and different countries. This is a paper that came out early on in the pandemic. And the paper was basically a paper about the origins of COVID, which is an ongoing discussion and debate. We may never know. There's theories saying it did come out of labs, some that say it's not. That's, it's an ongoing research question. We don't have answers. But this particular paper claimed that there was some similarity of unique inserts in the COVID spike protein and HIV, which was kind of, at least from this paper's perspective, potentially evidence that it came out of the lab. Now, this particular paper was published on what's called the bioRxiv. It's a place where scientists place articles before peer review to get feedback and to get it into the public conversation faster than it takes to go through peer review. Because peer review in some fields, like in economics, for example, in some areas of social science from which I work, in addition to other areas, it can take 5-6 years to get peer reviewed. And during COVID, we couldn't wait that long. Now, this is the bioRxiv. There's another archive that physicists use called the ARXIV. It was the ARXIVarchive.org. It's out of Cornell University, started by a colleague of mine, Paul Ginsberg. He started it in the 1990s, and it's been used by computer scientists, physicists, and other fields that have been using the archive for decades now. But the life sciences just didn't adopt the archive, which I'm a support of the archive, by the way, because I do think it's a way of getting things out quicker, at least putting it into conversation. But the key thing about the preprint archives is they're not peer-reviewed. Now, it doesn't mean that they're all low quality. Some of them are very high-quality papers that are published on the archive, and sometimes people don't even send them through peer review because they're off to the next thing. It doesn't mean it's good or bad. A lot of times you get very good quality articles on the archive. They just haven't been peer reviewed. That's the key point. So if you ever see articles in the news, and it happens often, science journalists will cite an article or reference an article that was supposedly published, but it was published on an archive. So when you look at that paper, you can still look at it. It could still be a high quality paper and worthy of the attention, but you should have in the back of your mind, it hasn't gone through the formal channels of peer review, which would do some of the checks. It's not perfect again, but it would do some of those checks. Excuse me. But the main thing is that it's now been officially adopted in the life sciences now. This was just from the pandemic. This is relatively recent. The bioRxiv is a new thing, even though it had been very well used, a different version called RXIV, different website, different university, in other fields. But this was a big improvement in science communication. However, now I'm getting back to this paper. This paper was shared all over the world, and it was shared as if it was a peer-reviewed published article. Not too long after it was posted, even the authors themselves admitted some problems. and it was withdrawn. That's what you see on the website now. It's a very small box, just like the one from New England Journal Medicine. They need to make these bigger boxes, big, huge letters, not small letters that you can barely read, but it says, this article has been withdrawn. Click here for details. And yet it continued to be talked about in the public as evidence. And again, we're still in debate. Like, it's not that things have been solved. There's been good papers similar to this that have been published about lab theory and non-lab theory and all these other things. That's an ongoing research question. But this article shouldn't be used anymore, and it was continually being used. This number to the side, 14,900, is basically a way of measuring its spread across the world in social media and in traditional media. And this broke records at the time. It was one of the most shared articles of all time. And that was partly because the public wasn't prepared for the preprint archive. And even science journalists and journalists themselves weren't aware of this new form of science communication. But you are now. So you're going to be aware of these archives. And again, it doesn't mean they're not good articles. Many of them could be better than a lot of articles in the peer review. It just means they haven't been peer reviewed. All right. As I mentioned, here's some resources that you can look at here. All right. So now let me look to some very kind of more specific elements of digesting some of the research that we see all the time. And let me start with a statement that I've learned over the years in studying this and also teaching about it. That correlation doesn't sell headlines, but goodness, causation sells beautiful headlines. It sells headlines. It makes them more clickbaity. And so let me give you some examples. Well, let me just show you an article. This is really interesting. So there was this research article that looked at the 50 most shared research studies of all time at the time that this article was done. And what the researchers found is that half the news articles by the journalists misattributed causality based on correlative evidence. Now, it's understandable because humans are actually very bad at this. We're not good at it. I talk to students about this and they're like, I know, professor, correlation doesn't necessarily imply causation. I know. And I'm like, okay, let's do some tests on this. And they find that it's very hard, even for science journalists. But here's the key thing to pay attention to. A third of the journal articles by the researchers themselves misattributed correlative evidence for causality. So what does that tell you? It tells you that even the professionals have a hard time with this. So we need to be looking out for this, and we need to build better mental muscles when trying to discern true from non-true. So let me show you one of the more viral spreading kind of news examples. There was lots of them. We can track these things in our center because we do these things. This one took off in all sorts of languages. It was here published in Forbes, published everywhere. It was based on a real research article in a good peer-reviewed journal. And it claimed that bald men were at higher risk of severe coronavirus symptoms. And you can imagine this really, took off, and it was all over the web. But there was an issue. And of course, as you can guess, it has to do with correlation and causation. But I want to mention that this was in a really legitimate, this is not one of these predatory journals. This is a good journal, Journal of the American Academy of Dermatology. This is one of the main figures in here. It talks about this, its possible targets, and this androgen pathway looks, like they'd really sort of thought through this. But the journalists, the editors, the peer reviewers, and the authors missed something pretty important. And I'll give you a clue. It's a common cause for both balding and COVID susceptibility. Anyone can think what that common cause would be? Oh, you would all get A's. So they don't even have to do any more of the post quiz. They got it there. That's good. You got it. So their hypothesis was that baldness was causing COVID risk, and there was this endocrine involvement into COVID pathogenesis, but they forgot age as a common factor. And Forbes had to retract this, as did many, many others. So I give this example because, whoa, you got it right away. It shows that you can do this too, but that many of those in the process of communicating this result forgot this. But it's an important issue. And as I mentioned, correlations don't sell papers, causation does, but that's not how it translates in the public. Correlations are not prescriptive, but that's how they land. So a science paper would say, like, moderate consumption of wine is correlated with reduced risk of heart disease. That's what the science paper might say, but that's not what the news report will say. The news report will say red wine consumption reduces heart disease. You see the difference there? And the prescriptive claim, even probably worse than that, reads more like this: drink a glass of red wine, which I love red wine, by the way, with dinner to stave off heart disease. Now, it may be true that red wine is good for it, and I hope it is, like I said, because I like it. But that's like a general way in which these things go from news article or like research article to news to prescriptive claims. So the cautionary note in the lesson there is that correlations sell headlines, or correlations don't sell headlines, causations do. Now, when thinking about this, I want you to remember the black box schema here. This is an important thing I talk about in the book that I mentioned, that you don't need to have a PhD in computer science or statistics to be able to push back on data claims. And in science, we quantify basically everything in many ways, which is a good thing in science. And it's a powerful tool that we apply to our questioning of the natural world and the physical world in which we live. But I really want to empower all of you, and I try to do this in the book too, to say that you don't need to know much about the statistics. You don't have to know what's in the statistical procedural box or the machine learning algorithm. You can just ask questions about the data. And let me give you an example of how you do this. So there were claims during the COVID pandemic about the utility of using AI to detect things like pneumonia. Sounds remarkable, right? And it really is remarkable. Imagine you could use some computer vision techniques to detect where someone has pneumonia or not. And the idea here is that you would, there's association potentially between disease state and image features, and the system would learn how to correlate between this disease state and image features. That maybe the machine could see something that radiologists, for example, couldn't see. And if the disease state is causing these image features, the AI will be diagnostically valuable. That was the sort of claim. But before I show you any of the papers, and before I show you, any of the sort of procedures, the machine learning procedures used, you could push back on this. I'm going to walk you through it so you don't have to, if I had time, I'd sort of test you how to do this, but I'll just look at this quickly. The question is there a breakthrough? Maybe, but you have to ask the right question. What is the AI actually looking at? It turns out some colleagues actually here at the University of Washington too, and various other places, kind of showed what the AI was looking at. It wasn't looking at anything about the etiology of the disease or anything about the pneumonia itself. It was looking at things instead about hospital state. Like, was the image taken in an outpatient setting, or were they taken inside, an emergency room? And what the AI was detecting was nothing about, like I said, the actual pneumonia. It was looking at whether it was a supine position where, because they were in more serious condition, or all these factors that really had nothing to do with the exact disease state. They were informative, but you could ask those questions and be able to call BS a little bit on the abilities of the AI system by just looking at how the data came into the system. So looking at the data, say, well, show me the data that's coming. Oh, but look at these features that it's seeing. So it was looking at things like supine and whether it was, again, outlook. So there's imaging procedure, hospital. This is a way of applying this black box procedure. But let me show you another one. And this is again on one of the topics I absolutely love. In fact, could write an entire book about selection bias. And this occurs when you essentially sample from your representative sample, or your sample doesn't represent the population by which you're trying to learn from. So it occurs when people, or whatever your sample, differ systematically from the population at large with respect to the question you're asking. So you want to understand about, like, if I want to understand something about this room and I only sample a couple of you, but the couple I sample are just the people closest to me, or the people that wear glasses, or, if I make decisions that create a biased sample, that creates biased answers. So during the pandemic, one of the other, things that went viral was this question that, were masks causing cavities, essentially. And there was a set of dentists in New Jersey at the time that said, hey, we're worried about mask wearing because the patients we're getting right now in the early part of the pandemic, they're all having severe dental issues. So maybe there's something about the oxygen exchange that's causing this. Now, of course, that is not what was going on at all. It was a selection bias issue. Who goes to a dentist in the early parts of the pandemic to just do a routine check? The people that go to the dentist in the early parts of a pandemic can't sleep at night because their jaw hurts so bad or whatever. So that's what they were seeing, was a biased sample. So it wasn't that they were seeing a higher frequency of people with awful cavities or dental issues. It was that they just simply had not, they just were sampling. There was a strange bias to their sample. I'm going to skip this example. I love this example, but looking at time, I want to make sure I give enough time. You can read more about it on my website, but it's basically something called left censoring bias, where there were claims about, certain kinds of music genres being, worse than war. Anyway, I'll let that one go because it's a really great one. But I do want to say this, that of the mistakes that I've mentioned in science, that we should subscribe to Hanlon's razor, which is never ascribed to malice, what can be adequately explained by incompetence. And even better than that, because we're all in a little incompetence sometimes, and never ascribe to incompetence what could be truly understandable mistake. And some of these examples I've said are just truly understandable mistake. All right, so I've gone through these lessons and cautionary notes, but I can't have a talk about science and communication and sort of misinformation without talking about the elephant in the room, which here is the elephant, generative AI. So generative AI is, I can tell you this, like pretty confidently, that AI is making things even more challenging, of course. Partly because you can just simply, generate lots more content, which makes it harder to discern what is good information and what's bad information. But also because bad actors are employing the technology, for sure. But let's just move the bad actors to the side for a second. Just look at the ways in which generative AI is affecting the information system more generally. In science, it's become incredibly overwhelming. We couldn't keep track of it before generative AI. It's getting harder and harder, and it is being employed in science. And I could talk about how it's being used in the doing of science, but also in the communication of science. And there's some examples that I'm not so proud of for science. So I'll give you an example here. So this is a paper published by Elsevier, one of the largest publishers in the world. This is a legitimate publisher, although it's not to say that everything is legitimately published there. But these and others have been called out recently for what we have found in the introduction. Let me just read it to you. Certainly, here is a possible introduction for your topic. What does that sound like? ChatGPT. So this got through all these authors, the peer review and everything, and they didn't catch this obvious insertion of ChatGPT talk. And then the other one is, I'm very sorry, but I don't have access to real-time information or patient-specific data as I'm an AI language model. I can provide. So essentially, these introductions were thrown through ChatGPT. And maybe the introductions are reasonably okay with references, but it wasn't noted at all. And this is a problem as we go through this transition and using this technology. So it is making it more challenging. Now, I was just going to say, I kind of truth is there's this overwhelmingness, and my colleagues and I'm on a board of a project, a new startup, which is trying to basically bring the scientific literature to the public. So if you have questions that you want to ask about the literature, you can go to what's called consensus.app, and you can ask questions that give you more than just one paper. So if you asked about the wine, for example, it would come back and say, okay, there's been 342 articles that say wine is good for you. There's been 322 that say they're not. And so you get a sense that there's a mixture of results. And so we can then see, at least with some questions, whether they kind of reach consensus. And this allows you then to get summaries. And again, full disclosure, I'm an advisor on this project. So, I'm showing it, but it does, it's an attempt to address some of these overwhelmings. Now, it's not perfect and it doesn't get everything right, but it's a way to bring the scientific literature more closely to the public. So you can check it out. And if you have questions, the group that's doing the day-to-day stuff is hopefully responsive to that. So that's different than what I'm talking about here. This was more sort of a tool to try to address some of these issues. This is some of the things that we're seeing. And also, it is beautifully, it's so good in so many ways, it basically BSing anything. So I asked it to give me some citations, and it gave me these citations that look like papers I've read, but they haven't. They're obviously not papers I've read. So instead of calling these hallucinations, some of my colleagues have been calling them hallucitations, which I think is a great term for what's going on here. It's a great little mimic. But one thing to be a little aware of, when you start to look at the ways in which these LLMs are using references and building on knowledge as we do in science, be careful about what those references are how those references are laid out. Because What they're not doing is what we tend to at least try to do in science. We don't always do that, but we're building on the shoulder of giants. This is a famous sort of quote from the philosophy of science, where we look at the literature, we build on it, and we reference, but that's not what LLMs are doing. They give you an answer, and if there are references, because they were criticized early on, and we were some of the groups criticizing, saying, how do I even know where you got this information? So then they said, we'll start adding references. But those references are done post hoc. They're done after the fact. They're looking at semantic similarity, essentially. So those aren't references that it's coming up with, and it's very difficult for it to actually identify where it's getting those answers. Now, there's things that researchers are trying to do and engineers. It's not like, we're done with the problem, but that's very different. I just wanted to note that. And I want to note also that it's become incredibly challenging to discern some of the more reliable things, even on traditional search engines. So my student and I wrote a post a month or so ago talking about the ways in which traditional search, so Google search, Bing search, are colliding with this new form of search with LLMs and chatbots. And so, of course, search engines are the window into what we're looking at. But if you asked a question like this, by the way, this still is up there, and I've talked about it, and I don't think Google has fixed this one, but this demonstrates how brittle some of this process is and how sometimes unrivaled. So if you ask this question, is there a country in Africa that starts with K? The top thing that shows up, which has this legitimacy, right? I was like, oh, well, it's the top thing on Google. This is what it says. If you go and search this now, this is where you're at. While there are 54 recognized countries in Africa, none of them begin with the letter K. The closest is Kenya, which starts with a K sound, but is actually spelled with a K sound. It's always interesting to learn new trivia facts like this. Now, the reason that came up is this website in which Google was scraping data was generated with was generative AI content. And it was hallucinating, of course. But yet Google then thinks it's legitimate. It doesn't know whether it was human generated, so it's just throwing it up, and it throws it to the top as a snippet. And so this sort of thing is happening all the time. We've actually shown in this post that we did that you can find at the CIP. So go cip.uw.edu, which I can share after. We have a bunch of resources to look out for things like this. And this has this post about search and other things that you can learn about. Excuse me, but some of these new search engines like Perplexity, which is a new thing funded by Jeff Bezos and others, the CEO was quoted as saying this, which kind of bothers me. It says, if you can directly answer somebody's question, nobody needs those 10 blue links. And I'm totally disagreeing with this. You absolutely need the ability to source information and figure out where they're coming from. And so if I search like Faktabar, for example, I was just in Finland recently talking about media literacy there, and this is a fact-checking agency. So I wanted to look it up. I wanted to be able to go to the source to learn more about it. And now, because one of our colleagues, Mike Caulfield in our center, has been pushing Google for about 3 or 4 years saying, please give the tools of fact checkers to the public. So now you can go and you see these little 3 vertical dots at the top of each one of the searches. You can find this now in your search. You can use those to get information, metadata about the website. So you can now click on those 3 dots, and they've kept that. Actually, Google's been happy so much with this new thing that we were trying to push them to do, that Mike Caulfield, who was in our center, was trying to do, that now you can get it. So if you click on it, it'll show you when it was first indexed. So this was first indexed in 2014. It can give you other kind of information. So any metadata that they have, you can use it. And this is what fact checkers get, or they're trying to look for. Now you can get that quickly. And importantly, you can now, this is just recent, you can do it on images. So I always talk to people about the shark swimming in the street. This year, we're going to have a pretty severe hurricane season. And I can guarantee you right now, I'd be willing to bet $1,000 with any of you want to bet that we're going to see the shark swimming in the street image. It just always comes up. In fact, it's the same one. A lot of times it's this one, but it's different ones too. Although there was one year when there was actually a shark swimming in the street. So you have to be a little careful. But okay, most of the time there are not sharks swimming in the street. And if you click on the 3 vertical dots of this image, it'll show you a fact check by Snopes, others saying, no, this is not a real image. It can tell you that this version of the image was 10 years old. So if you saw if a hurricane happens tomorrow in Florida and this image shows up, you can say, it's not, like, maybe there are sharks swimming in the street there, but it's not this image. And that, so watch out for those kinds of things. And so these are debunking inoculation. So I'll end. This is an image of a museum in San Francisco that I took my family to and just absolutely loved it. It's a science museum. And it really sort of, like a lot of these museums, really show how magical science really is. And so I want to end, despite some of these issues that we're kind of, growing pains we're going through in terms of science communication, trying to discern what's true or not. At least you'll be aware of some of those things. I couldn't go through, of course, hundreds of hours of more things to talk about. But I just want to end with, despite some of these challenges, science works remarkably well still. And we can still fly in jets. We have, marvelous medical, magical things that, medicine. And it's really just an amazing institution. So with that, I'll end. Thank you so much for coming and spending the time. And I'm happy to take any questions, but I know we're probably ending. So thank you so much.